Uh, so my name is Ram, and we should start with a quick poll right here. So how many of you consider yourselves to be like security engineers? Okay, that's great. I just want to make sure. How many of you consider yourselves to be machine learning engineers who worked in machine learning? Perfect. I see like John's hand go a little bit. You got to raise it up, man. So that kind of helps me orient. So here's a familiar scenario, whether you work in machine learning or in security. Imagine Friday evening, you're out to go, and you're now on call, and unfortunately you have been held back. The login anomaly detection that either you built or you most likely inherited is spewing a lot of false positives. Your incident responders are not happy, and you're like, oh my gosh, the security analytics system is broken, sev to incident, and your page is going off. So there are two things that could have probably happened. The first one is the security assumption that which you had built your system is changed. Say, let's assume that there was like a important vulnerability, and your service engineers just went right in and patched it, and that kind of like bricked all your computers, and now there's like a failed logins because of your cell phone, which is causing this like massive amount of like false positives. And if you think, this is something that actually happened to when I built my first login anomaly detection. And because service engineers, their job is to fix stuff. And they don't tell you when they're fixing stuff, especially if it's a critical vulnerability. And this is like, a small graph of like, how I feel the security landscape is always changing. So on the x-axis over here is, the time, the number of days. And the y-axis is the number of like high security vulnerabilities. So it's pretty much I create the CVE database, and I looked for those vulnerabilities that are scored 7.5 or greater. So it's an OS level like system, and attacker can run arbitrary code. It is very much possible there was a patch for one of these CVEs, and this being high priority probably got patched through. So net, your security assumptions always changing about your system. Alternatively, the analytics assumption with which you built your system could have also changed. And this is because the fact is like the machine learning landscape is also changing rapidly. And a good example of this is the TensorFlows, like major feature like breaking API changes. So TensorFlow is essentially like Google's big bet on open source like differentiable programming toolkit, and there's a lot of open source contributions, and that tool is very rapidly evolving. So if you, by the way, again over here the x-axis is the timeline, and the y-axis is the number of like major feature like or like breaking API changes. I just restricted myself to that. If you're wondering why September's got like no changes, they only had like a GitHub. There's only a GitHub deployment, so the binaries were still the same. And December probably was low because of code freeze. But you can kind of see that they make breaking API changes all the time. I just picked TensorFlow, but this is the same with Microsoft's Cognitive Neural Toolkit or any like system out there. For instance, like they might push out a new learner, and your applied ML engineer who's developing the system might have swapped out learner, or they might have retired a feature, like tf.pack got replaced with tf.stack. So if you use tf.pack, it's probably going to be broken, and that could have caused like this breakdown. And the fact of the matter is just like how security landscape is changing so much, and because the machine learning landscape is changing so much, you also have these plethora of tools that people use as different tool points. You might use R for like prototyping, then you might use like TensorFlow for deployment, or if you want to support Microsoft and increase its stock value, you'll use CNTK. So different parts of the pipeline use different parts of the tools. And today I'm going to talk to you about some of the experiments that we did in platform security and how they failed. My goal is definitely not to get through the slides, so I'll make sure that I finish much earlier and you have time for questions as well. So in terms of like the textbook machine learning development, like you might think of this is a life cycle that you might generally see. people first they would try to define the task, they would define the data, and they would use like some sort of like machine learning model, and then they would get the result and deploy. And this is like, whenever you hear people talking at at a conference, you might assume that this is the cycle that they went through. But in reality, industry-grade like machine learning solutions are extremely exploratory. Like there are many, many attempts that happen in the background, and the one that people generally talk about is the one that succeeded. And you never know like why those other attempts failed. Did it fail because like it didn't meet the the metrics that the program manager defined? Did it fail because it wasn't scalable? And I feel like the aim of this talk is to share some of the experiments that we did that did not ship, and share some insights about like why they failed. That's basically the takeaway. And essentially, like I have 3 failed experiments that I want to share with you. And for each of these failed experiments, I'll go through, hey, what's the problem that we started to solve with? What was the original solution? Why did it fail? And how we improved on it. So this is kind of going to be the theme that you'll see throughout the talk. And finally, I'll wrap up with how do you actually go from experimentation to production? So, there's a slew of great talks today at BSides Las Vegas. I'm personally excited about the Powershell talk that's going to come pretty soon. So, one of the things you want to keep in mind is how learn the technique that the person probably shared with you, and think of pushing it in production, because that's how you're going to add value to your business. So, jumping right into case study 1, the lateral movement detection. So lateral movement, just make sure we're all on the same page, is when the attacker like moves laterally within your environment to attain the goal of either say credential exfiltration or even cause havoc. So they might first compromise a dev box through phishing. From the dev box, they move into production because, hey, we're all DevOps, right? So you have like some sort of like constant access to production, and they move laterally through the environment before they attain their goals. And the problem that we want to solve is, can we detect lateral movement? And this is a really important problem to solve, especially if you're a machine learning engineer and this is a term that's unfamiliar with you, because once the lateral movement stage has been reached, it's pretty much difficult to detect an attacker because they go under the radar or they blend in. Meaning there's so much, I feel it's a code word for there's so much of noise in my system, I wouldn't be able to like detect the attacker. So you really want to be able to detect lateral movement before they actually attain their goal. So I'm going to discuss like one experiment that we did to do this. And actually, this was something that's actually in production for on-premise, and you'll see why. So what we intuitively did was we built separate models to detect our goal of compromised accounts. So we want to be, our goal is, when an account is compromised, you want to be able to detect it, so you don't even go to the lateral movement phase. And we built a suite of models, and the crux is that each model kind of independently assesses if an account is acting suspiciously. And I'll go into like what the models are in just a minute. But the data that we use is the Windows security event data. So on average, like an online service like Office 365, just to give you a scale, produces like 30 billion sessions per day. And that roughly translates to 82 terabytes of data. And essentially the data that we're looking at is the sequences of like Windows security event IDs. There are roughly 367 of them. That's what TechNet says. We've kind of whittled it down to like 14 of that as of major interest. And what kind of sequence are we looking at? We look at, hey, if a user is logging into a machine, this starts a process. The process must exit and the user logs off. So, in a very infrastructure setting, it must be very, very constrained what especially a user or a service account does. It's not like, me in my dev box. So I told you that we built like, an ensemble of models. And here's what the model looks like. So we look at it from a session level. So we don't look at it from a record level. We look at a session, and like I said, a session is when a user performs a sequence of actions. And for every this is a representation of some of the models that we built. So one of it is like, what's the probability of this account logging into this role? If it's a user who's always logging into, say, a SQL or a web front end, and all of a sudden now they're logging into a domain controller, hey, that's like super suspicious. Or what's the probability of seeing these sequence of events? And this is kind of the ulterior motive of this question is to ascertain if it's a service account or not. Service accounts are automated accounts, and they must be only performing a very certain narrow subset of activities. So you log into a box, you kick off a process, and then you get off. There is no like browsing around over there. So we look at the sequence of events. The third model, for instance, is like, what is the probability of this account like elevating its credentials? Again, from an infrastructure security perspective, if you ever want to elevate your credentials, we have a just-in-time system. You can't just right-click and run as admin. That's a big no-no. And the third thing is the last one is hey, are these events auto-generated? Especially from a service account perspective, the time interval between two events must be pretty tiny, because there's probably a PowerShell script that's automating these service accounts. And when a red team goes after service accounts, and they love to do that because it's got lots of permissions on a lot of boxes, the time interval between those events are no longer same. So that's another thing that we kind of look at. So we basically have a lot of models estimating independently what's the probability of this account being compromised. And this is what end of step one looks like. You've got a session, and you estimate these probability models. But where we really want to go with is, hey, we want to get some sort of combined score. We want to be able to look at, for all these, from different perspectives, what is that account's probability being compromised? And you want to weight them in some sort of interesting fashion. You just don't want to do some sort of linear combination. So the way we combined them in our experiment was we used RankNet. And RankNet is a supervised learning to rank problem. So think of when you go to Bing, and if you ever do, you would, and when you search for a query, you get a list of answers to it. Those answers are rank ordered based on relevance. So the RankNet was the initial, even before Bing G8 is, RankNet was the initial algorithm that was powering that. And it does pairwise ranking, so it's really nice. So as opposed to comparing between two lists, it tries to optimize for pairs. And so we try to take RankNet, and I put a pointer to the paper right there. So imagine that you have two sessions, a malicious session and a benign session. And that's your input. And then you also give RankNet a probability. And the probability, it's what's called relevance score. So if you set that to 1, RankNet knows to put the malicious session on top of the benign session. And if you put 0, the opposite occurs. And this kind of property not only you'll see helps to combine, but also gives a rank ordered list for security analysts to evaluate. When you're giving a set of alerts for security analysts, they like it to, they kind of expect the one at the top, or they would have budget for top 5, top 10, and the hope is the one at the top is pretty much where they have to invest the bang for the buck. So RankNet also helps solve that problem. So during training time, or when you give the 3 inputs you give to the algorithm is whether it's a malicious session, a benign session, and a relevance score. And you get a function that if such that hopefully the malicious session is pushed to the top, and benign session is pushed to the bottom. And this is kind of how RankNet works. You take the malicious session during training, and then you push it through the probability models that I spoke to you before. You get a bunch of probabilities. You take a benign session, you push it through the probability models, you get probabilities, and you set this bit to 1, so RankNet knows to get like, the malicious session to be ranked higher than the benign session. So, and out pops the weights. So that's pretty much like how you go from there. You get the weights and you put it in the model. And this experiment was super successful for on-premise systems. In Office 365, this is a running model from an infrastructure security perspective, wherein, showed a couple of times how it's been validated with red team attacks. So, when we built this model from an on-premise setting, and we expanded it very bravely to the cloud scenario. And I got this very nice email from a security analyst, and if you can read it, the only 2 things you should kind of like note is that it's at 3 a.m. and the word anomaly comes in parentheses. It was like, please shut this off, which is code word for do it or else I'm going to kill you. Because there was so much of noise in the system activity, and it's all expected and not security related. So, comes to the exactly womp womp. So why did it fail? We did our best. It worked so well in on-premise, and we expanded it to cloud and hope it would work as well. So, first thing is security assumptions pretty much changed. If you look at a traditional on-premise setting, a production environment, which most people are familiar with, it's very nice. You've got this private network. It's your baby. You've kind of enclosed it in an eggshell. And inside this eggshell, you've got all different types of servers. And every server, if you want to host some sort of database, you spin up a SQL server. If you want to host files, set up a file server. So, and these are all physical machines, and you pretty much add them to the domain via the domain controller. And there's one central place of truth. You know exactly where your crown jewels are. We've been told time and again that, hey, if somebody can pop your domain controller, they've got keys to your kingdom, and you're pretty much done for. Which makes a lot of sense because in an on-premise setting, you know exactly what to look for. But let's come to the wild, wild west of Azure. So Azure is in a cloud services setting, pretty much everything is a service. So whatever you thought of as a server is like a service. So you've got a SQL server, you've got Azure SQL to mirror it. You've got file server, you've got where to host, you've got Azure storage account. One of the things that fundamentally shocked when I joined Azure was that there is no domain controller. There is no one central brain like the domain controller that's orchestrating it. So one of the things that so we had to first kind of think. This is a big paradigm shift for me. 4 years back, as to how moving from on-premise to cloud means looking for different sorts of crown jewels. And one of the things that you will notice is over here they're all physical machines, and they're all things like the Windows security event logs are our bread and butter. But over here in the cloud service setting, a VM or the host machine is but just a small piece of the puzzle. Windows security event logs are still valuable, but there are other sources of logs that speak truth. So that was a second realization for us. And one of the things that you want to keep in mind is just how you would think of something like passwords, have a very different paradigm in Azure. So you talk in terms of certificates and storage account keys, and where you think of here as LSAS, it's almost mirrored to as key vault, where you store those secrets. So mapping these things was super important for us when we moved from an on-premise setting to cloud setting. And this is a fantastic a translation diagram that our red team, Andrew Johnson, put together, which kind of helps me when I'm building detections for the cloud, help me translate things. So any concept of domain, just how you want to protect the domain. the goal in like infrastructure security, cloud security, is to protect your subscription or to protect your tenant. What you think of as pass the hash in an old Windows setting, in a cloud setting is credential pivoting, where you harvest credentials and you reuse those credentials to see if you've got any kind of access. So the big difference is like any time that you're going from one paradigm to another, it's really hard for you to like reuse the same technology. I'll show you give you a little bit insight into how we solve this problem in just a minute. So, this was just to prove the point that over here you see a new process is being created in the context of an on-premise setting, and this is like a process creation in the context of like a host setting. Wherein over here it's you pretty much everything would run. You would get like an account name, for instance, and from over here because it's orchestrated from an infrastructure perspective, it's system. So you're not going to glean super big insights just by looking at account names. So how did we kind of like improve our failed system? So the first thing that we did is we translated the quote favorite kill chain and adapted to the cloud. So like I told you, in an on-premise setting, an attacker might compromise somebody's credentials and then get hold of the service account and use that service account to ultimately like move laterally and get to a domain controller. In a cloud setting, they would start off with compromising a cloud developer account, and then instead of like we translated a concept of a service account, we mapped it back to what in the cloud is a service account, and it turns out there is something very equivalent to service principal. And just like how the goal of an attacker might be on-premise to become domain admin, over here it's subscription admin. And we also increased the visibility of our logs and not just relied on host security event logs. So we expanded to, for instance, like the Azure Resource Management Manager. That is kind of like, think of it as one of the brains that's controlling the cloud in terms of like anything that is important. So if you create a service principal, or if you create a storage account, or if you modify permission, gets kind of like added to this particular log source. So this was super vital for us. So I'll give you a quick overview of this particular technique. So essentially what we did was we used the service level detections and we converted it into a graph. And essentially the graph is nothing but every node is pretty much an entity in terms of like, it could be a user account, it could be an IP address, and an edge is something that's connecting between them. And what we did was like, you can kind of imagine that because we have so many millions of signals, this graph is extremely big and untenable. So we pruned the graph we constrained it using our kill chain, and we constrained it using like a stochastic process. A random walk is a great example. And that kind of like, helps us to go from like millions to like a handful of hundreds of possible attacks. And then we just pretty much score those subgraphs using things like random forest if you have labels, or else we do spectral clustering if you don't have labels. So in terms of like performance, the biggest thing that you want to take away is that you had a lot of our false positive rate kind of like dipped, and we got a 6-point improvement by using this. So if you take away from this case study, the important thing is when you're changing paradigms, it's important for you to think about not reusing the same solution. So that's like the big takeaway here. I'll move through this one. So in terms of like the second case study is like how we wanted to detect like PowerShell attacks. And you pretty much know that when you get like a suspicious document and you click on it, here and there's this like macro that's running like a base64 encoded command, and you're pretty much like done for at this point. And there's like PowerShell attacks are really becoming common because like, hey, guess what? If you're like want to go after like a Windows system, PowerShell is like natively installed. You don't have to do any sort of installation from a toolkit perspective, and they're all like, they don't even touch disk. So there you go, perfect. And there are a bunch of toolkits out there that kind of make it even even more easy for attackers to go over this. So in order for us to do this detection, the way we think about it is we take a malicious file and we detonate it, and we essentially collect the exhaust from those logs. So we look at timestamp, we look at the command line, and we look at a host of those other information. So the first step that we did was we try to build, we try to estimate the transition probability. So we first took the syntax, we extracted the syntax trees, and we thought, hey, Internet Explorer should not spawn, say, command.exe. That's really suspicious. And we essentially try to calculate, what's the probability of the current command line happening just by walking through this Markov chain. So when we try, so this from a logic perspective, it made sense to us. People shouldn't be doing unusual sequence of events, and the command line should pop up. But ta-da, this also failed for us because guess what? Daniel Bohannon, I think, gave this wonderful talk about obfuscation, obfuscating command line. So just to kind of you're not familiar with obfuscation, this is the command line that they want to, attacker would probably execute. But after obfuscation, you can see there's a bunch of parentheses and a whole lot of things which still, through the magic that is PowerShell, still executes, but it's very, very difficult to detect. And our Markov chain failed because, first of all, the first thing was why can't you just use rules? And you cannot use rules to detect this because the number of regexes that you're going to write is going to be too much. And classical systems like Markov chains do not work in this perspective because every command is unique and there is no the proverbial pattern for you to discern. So we did not have, rules didn't work for us, and our existing system, pretty much experiment that we ran kind of failed, and we tested with real data. So the way we improve this, and this is a paper that was just published by my colleagues. So they use character convolutional neural nets, and I'll just give you an idea as to how this works. So you essentially take the PowerShell commands and you convert them to bitmap representations. Think of it on a very high level. And deep neural, convolutional neural nets are extremely good at identifying images, classifying images. So facial recognition, if you use Windows Smile or any of those things, are pretty powerful because they can capture hierarchical representation of your faces. So the way they think is they take an image of your face and they decompose it into kind of edges, and many edges will become contours, and many contours will become a feature like a nose. So think of them as converting to heat maps, wherein the stronger, the more red the color is, the higher the value of count frequency. We pass it through a deep neural net for classification, and I'll be happy to point you to the paper. And essentially what happened was we were able to get a huge improvement in terms of our true positive rate. And one of the things that those guys proved was that they maintained the false positive rate constant. So for a comparable, and this is important from a customer perspective, especially when you're deploying new systems, is if you're increasing the false positive rate, simultaneously increasing the true positive rate, they still don't care. It's still more alerts in their queue that they need to triage. So this is another example when we have a system that worked for attacks that we knew of, but because the security landscape changed so much and there was command line obfuscation technique became really popular, and this system kind of our existing experiment did not work. So we had to kind of change our strategy as the landscape was evolving. The third case study that I want to walk through is how to detect geologin anomalies. And this is kind of a very common problem, especially if you're running an infrastructure from an infrastructure security perspective. Somebody's always logging in from Vegas, but all of a sudden now they're logging in from across the pond in, say, some part of China, you want to be able to detect that. So intuitively, and this was like our first pass, was, hey, we cache the last 10 locations of the user. You know, users generally do not travel as much, except for like, and for the current location, you know, if the current location is not part of our cache location, then we challenge the user. We tell the user to kind of like, you know, we trigger like multi-factor authentication, or I'm sorry, we challenge the user in terms of like SMS, or just like how, you know, Facebook would, you know, show you pictures of your friends, who, if you're like my aunt, she tags like random pictures. So there's a picture and like, is that your aunt? I don't know. She tags weird pictures. So, and if there's a false positive, then you kind of like, you know, add the location to the cache. This was like our very first like experiment in terms of like detecting like false logins. And this is reasonable because like from an implementation perspective, this is like a matter of keeping track of state, which we're very good at doing. So, I feel like you should have figured out a theme right now, is that this one failed for the following reason. So first off is like, a problem with such an intuitive system is that, with the basic system, is that it does not account for complexities. So for instance, first of all, people do travel a lot. And if you have salespeople in the organizations, they travel a lot more than a developer. And beyond just travel, which is kind of easy to account for, there are company proxies. Companies have VPNs, and there are legitimate reasons why, you know, people use VPNs. You know, it could be for deployment in a data center in a different part of the world. And they also have like cell phone networks, which tend to be extremely noisy, especially, you know, if you're moving from two different, say between, say, Seattle to Portland, it still does not account for it pretty easily. And like I said, you know, vacations are pretty common as well. So instead of trying to like, you know, back engineer this knowledge, wherein we wanted to see if, hey, try to look at their calendar and try to ascertain if they're doing vacations, just turned out to be too untenable. So what we did was, oh, by the way, just want to tell you that even a modest 14% like false positive rate in terms of like, you know, Microsoft scale, wherein we have like 1 billion logins for all of Azure Active Directory, that's 280 million false positives. So think of like, you know, how much of trouble you're adding to the customers who are using this system, have to like sift through this. So in terms of like improvements, the key, there are two pieces of intuition that we had. First is, instead of like looking at a user from just in isolation, just looking at the last 10 locations, look at it in the context of their peers. That's like intuition number one that you want to get from the following slides. The second thing is like, how do they kind of like, is there a reachability score that you can calculate? So in terms of like the understanding the user patterns, so we capture like, you know, the past 45-day of login history, and we basically look at the frequency of counts as to how often they log into a particular system. And this is like users who are not been like no similarity metrics, and this is kind of like their cell phone networks that they connect to. The second intuition is that we try to calculate the user-user similarity. So it's essentially a huge matrix of like that we have, and we use custom similarity metric to ascertain how one user is similar to another. So the intuition is, if my boss goes to Israel because for work, and you know, if I follow up and go to Israel, you know, the fact that me and my boss are kind of in the same peer group, I should not get an alert or be challenged when I go to Israel. And from this, we use random walks with restarts again to kind of like ascertain the reachability score. So after we get the reachability score, we want to answer this question: how likely is a user in this location? And the intuition here is, if the reachability score that we calculated is pretty high, but So it takes them it takes them a long place to get there, say between Seattle and Japan. But if the time of travel that we saw was really short, then it's a problem. So that is what this shows. If the reachability, as the reachability kind of like moves to the red level, and if the travel speed also increases, that's really, really suspicious. So this is what it kind of shows. So imagine that you've got like 3 locations which we saw the users, and you see their time of like travel and the reachability score that we got from the previous step. We kind of use this as a transition matrix to kind of see, okay, the user is in Redmond, and now he's in Portland. There's also, it's still possible for him to still be in Redmond, but now that he's like, logging in from Hartford within just a span of like 15 minutes, that's really, really suspicious. So one of the most powerful thing, and if you haven't explored random walks, is that it can really drive the false positive rate really low because you can input custom domain knowledge as part of it. So this is something that we got a 70x improvement just by using random walks and trying to calculate a reachability score. So totally like recommend you to check this out. So I kind of like walked you through like some of the experiments that we did, and I wanted to finally finish up with how we take something from experiment to production. What is kind of like once we narrow down on like, hey, this is an algorithm that's got really low false positive rate, how do we put this in production? So like everybody, we start off with exploratory data analysis, just using custom tools. 18 applied ML engineers in our team, and each one of us has like our tool of choice. I use Python, one faction uses R. We had a new intern who came from school and asked if he could get a MATLAB license, and like we were like, what? So we first do like exploratory data analysis, and the first prototype that we generally do is we build one model for all set of users. And the problem with this is obviously if you have one model for all of users, you're not going to get like personalized activity. So then we kind of like build per user model for each for our population, and we try to like and the thing is like you cannot cram this all into like one worker role. So what we kind of do is we have a separate storage system for models. But then like you hit this problem wherein like you hit latency issues. So now you have a Redis cache inside so that you have some sort of LRU policy so that you're not like you're maintaining your latency commitments. And then our favorite part is compliance engineers come in and they're like, no, some parts of it is PII, and the platform cannot have PII. So what we do is we have a separate system that kind of has our PII data, which also has its own Redis cache, and that kind of communicates to it. So you can see that from our initial prototype to our final like template, it's completely like different systems, but we don't really start off with like trying to architect a Redis cache mechanism, because like I said, as you saw, the experiments tend to fail really well. So what should be like your big takeaways? So first of all, like when your security analytics system is broken, you have 2 things in front of you. Your security assumption could have changed, or your analytic assumption could have changed. But either way, if even one of them changes, you have to look at both of them. Like I showed you in the case of PowerShell, where like security assumption of obfuscated command line change, so we had to kind of like re-strategize. First of all, debugging ML systems is pretty hard. And I put a link to this paper, and they kind of like walk through like how you can debug a machine learning system. Well, guess what? Debugging security analytics system is harder. So here's kind of like things that when you go back to from the madness of Vegas and try to like make sense of it. The next week, first of all, there's an amazing talk yesterday. Thank you, John, for pointing it out, from CXO Sidekick. Totally recommend reading his slides. I personally like, it was kind of like if I were more sarcastic and if I had like, memes, that's what I aspire to do. So it was like 284 slides, but you can flip them through like, when you're traveling. I would totally recommend trying out Red Canary's like toolkit, where they help you kind of do unit tests. I mean, the way I look at it is they help you do unit tests for that, and really explore security as a service. That might also help you out. Next month, if you have access to a red team, go show them your detection. There's no shame in asking them, hey, this is my security system. Does my assumption still work out? And then, the next quarter, that's how we plan, in monthly and quarterly sprints. Look at things like how you can attack your systems automatically. Like Cloudy Kraken, from Netflix has like a bunch of capabilities. So these are all great tools for you to constantly see if your assumptions are still valid. And finally, don't ever think, detecting unusual logins is the problem. That's the prototype. When you operationalize it, you have to think about how are you going to deploy it with compliance restrictions? How are you going to scale it out? How are you going to evaluate and show to your management that this system actually works and is adding value? So, and don't ever discount, having, if you're running a production service, you want to have lifesite with on-call guarantees. There needs to be someone, if the system fails, who's able to step up and do it. So, my broader team has a bunch of personas that we rely on to ship a production solution. We've got machine learning engineers, but we totally rely on ops engineers for monitoring of performance, our compliance and privacy folks, our help us make sure that we're maintaining our commitments. I got product managers who go talk to the businesses and do our metrics. So it's not like a one-man security data scientist to get something into a production that's working. So that's pretty much the end of my talk. And if you're interested in any of the roles that I showed you, super hiring for my team and the broader team. You can always reach me at my email. I'm on Twitter. That's where all the cool kids hang out, but I just go there for sneaking around. But my DMs are always open. And if you have if any of what I spoke to you interests you, or if you feel like you can come and add value, I'm going to hang around. I'd love to talk to you guys. So thank you.
So we could take about 2 questions. Sorry.
Hi, what was your training size for the, let's say, the PowerShell attack?
For the PowerShell one, it was, I think, 400 gigabytes
A day?
Yeah, so that's basically all the exhaust that we get from detonating a suspicious file.
Thank you.
Yeah, absolutely.
First of all, very interesting talk. Thank you for presenting. And you mentioned you're collecting about, I think it was over 80 terabytes of telemetry from Office 360. It sounded like in your first case study you relied on labeled data for a lot of the training. Can you talk a little bit about the strategy for generating labeled data from that sort of volume?
Oh, yeah, absolutely. That's a great question. So there are 3 ways that we think of labeled data. So first one is we rely on things like our red team. So they would go after a service, and then we have the tainted records. That's easy strategy. That's strategy number 1. But the pros of that is that's as close as attacker data that you would get. But the con of it is for a service like Azure, not every service is going to get attacked every single day. So that's strategy number 1 with pros and cons. Second strategy is to kind of inject synthetic data. Now this might sound extremely trivial, but it really works as for you as a sanity check, especially it's a canary in the coal mine. So if your system has changed so much, and if your injected data does not pop to the top, you kind of know from a unit test perspective it doesn't make sense. The third thing that we rely on is try to have any sort of open source tools that especially our red team doesn't use. So we have out of test distribution to evaluate our system again. So we're not exactly only relying on one particular set of known badness. We've also looked from a completely like machine learning perspective. We have like 2 strategies. So first one is out of the box, things like SMOTE, when you try to like undersample and oversample. And the second thing that we've gotten good results with is we've got preliminary results with is using generative adversarial networks. So you have some sort of like data, the malicious data, and you try to bootstrap from that. So from a security perspective, those are the 3 things, and from a machine learning perspective, it's that. And for also like one of the things with Microsoft is because it has like products across the stack. So we've got like Windows covering, like the Windows team, covering the host level. You got Office 365 covering like application level. One of the things we do cross-pollination between products. So if you want to find out if a VM is compromised, and a hypothesis is like, hey, a VM is compromised if it's sending out spam data. So we get the labels, the spam labels from O365 and join it with our Azure data. So we also have this cross-pollination that's kind of different from the security and the ML strategies. Yeah. Oh, perfect.
And
thank you.
let's give a round of applause.
Okay.